So we're now moving to module number 13. I apologize, I'm drawing a total blank as to what the chapter is in the book, but this is still talking about sampling distributions. So that theme is continuing, but now we're estimating population proportions from samples. So in other words, we need to better, if we want to estimate a population proportion from a sample, we need to understand what is the sampling distributions for proportions look like. So that's where we're going to focus. That's where we're going next. So we're going to select a sample of size n. Oops. We're going to select a sample of size n from the population. Okay, so I left some blanks because I want to write these in a different color. So we select a sample of size n from the population. Okay, so n could be 10, n could be 1,000, n could be 15, n could be any number we want. Obviously, it has to be a whole number. If we have a binomial experiment, remember that essentially means two outcomes. I mean, there's more to the binomial experiment, but that's one of the key parts of the binomial experiment. Two outcomes, fixed number of trials, and the proportion has to remain constant. Then we assume there is some fixed population parameter, which we'll call P star. And here's where things are going to get tricky because we're going to start having lots and lots of different P's floating around. For the proportion of successes in the population. And I don't remember if I made a big deal about this, but when we talk about binomial experiments, we talk about successes. A success simply refers to a successful observation of that which you were looking for. So for example, if you're looking for fatality cases in a, for people that are succumb to a certain disease or not, obviously it's not a success that it was fatal, but you successfully observed that outcome. So that's the phrase, that's the sort of the terminology we use here. Now, when we're talking specifically about the sample that I obtain, so for my sample, I'm having the warm fuzzies. I don't know what the weather's like with you guys where you're located right now, but we've got one of these beautiful rainstorms where it's just beating down on the windows here and it just sounds heavenly. So my actual sample, we have K successes out of N trials. Okay. Now the notation we use here, is we actually write P with a little hat. And this equals K, the number of successes we had, divided by N, the number of total trials we actually did. Now again, in the notation here, this hat means the hat indicates it's an estimate. Okay, so the hat is just the statistician's notation for saying that we've got an estimate. Well, what are we trying to estimate? It's an estimate of what? We're hoping this P hat equals what? Yes, this is the proportion of the sample, and our hope is that this actually equals the population proportion, what we called P star. Now again, recall it's unlikely. It's unlikely. it's unlikely that p hat, our estimate for the population proportion from the sample, is going to equal p star. It's not impossible, but well, in some cases it is completely impossible, but just because it's impossible to get the proportion that would match exactly, simply because of the restrictions for our n, based on our n. But it's generally unlikely that the sample estimate does not equal the sample proportion does not equal the population proportion. Now, we don't really have a symbol for, so this is p hat, it's the estimate of the population proportion. It's understood that it's an estimate that comes from the sample, but we don't really have a notation specifically for that sample itself. All right, so any questions on that notation so far? All right, so I'm going to go ahead and clear this screen. So again, right now the notation is the p star and the p hat. We're going to want to keep those in mind. So what we're going to see is we can actually take advantage of the normal approximation for this particular distribution. In particular, the distribution of all possible p hats, the distribution of all possible p hats is the sampling distribution. So all the possible p hats that we could obtain, that's what we were referring to as the sampling distribution. Turns out that some of these sampling distributions are quote unquote nice. What do I mean by nice? Well, under certain circumstances, okay, so under certain circumstances, the sampling distribution of the p hats is nearly normal. Okay, so that's a nice feature that we can take advantage of. So under certain circumstances, this distribution is nearly normal. All right. Well, when is it nearly normal? Well, we kind of already talked about this when we introduced binomial experiments, but we'll go back and revisit it again here. So, so when do we meet this assumption? When is everything okay? Well, so p hat is nearly normal if okay, so the p hat are nearly normal if we meet the following requirements. Okay, so I'm going to write a couple of them. I'll write a couple of them out here. Okay, so one condition is the following. One condition is that the minimum of n times p star or n times 1 minus p star. If we take the minimum of these two values, this is the average number of successful observations. This in turn is the average number of failures. If the minimum of this is greater than or equal to 5, then a lot of books will say, well, okay, then you've got a nearly normal distribution, so it's perfectly okay to go from there. Now, a variation of this it's the exact same formula, but one variation is just to change this cut point. Some people will say that point should be 8, or maybe it should be 10. Those are the common values that are seen. So the point is that this value here is arbitrarily chosen. So consequently, you could pick different values for it. Now, our book uses a slightly different approach. Our book uses a different approach where it says if the variance from the population is bigger than a number, so that's where you take p star times n times 1 minus p star. If this count variance is greater than or equal to 10, that's what the book, that's the criteria that the book uses. Then it says that you've got a nearly normal distribution. This is a fairly stringent criteria to meet. This is the WAMAP usually uses this criteria. Sorry, that's an A. So WAMAP usually uses this criteria because that's one of the common textbooks. WAMAP was used for one of the common textbooks that we've seen. One of the common textbooks that was used at the time when we were building questions in WAMAP. This was the criteria that was popular, so we used that. But the truth is, it actually depends. So which one do you use? I actually can't answer that for you. It actually depends on the context. It depends on the criteria that you've been asked to use. Sometimes if you're working with a researcher, they want you to use one approach over another. So you just need to be aware that there might be different things that you'd be asked to do for these. All right, so let's actually do this. Let's actually do an assessment. So using this criteria, let's do a couple of evaluations here. Right, I'm going to go ahead and save this, and I'm going to go ahead and clear most of this. All right, let's see, I think I can, no, I probably better write this. All right, so here's the first problem. Let's do this one. So we have that n equals 12. We have that p star equals 0.4. I have that n times p star. So if I look at this, I know that n times p star equals 12 times 0.4, which is 4.8. And I can kind of stop here. I don't need to check for the other value. This is already less than 5. So I would say, sorry, in this case, the sampling distribution is not normal. So for this particular scenario, the sampling distribution is not normal. Okay. Now, if we do a different problem, all right, so let's do a different problem here. So let's do one where we've got n equals 25, p star equals 0.6. Okay, so I look at both n times p star. That equals 25 times 0.6, which equals 15. If I also then look at n times 1 minus p star, that's 25 times 1 minus 0.6, which is 0.4, which is 10. And then sort of regardless of which criteria we use, this sort of meets the criteria. Both of these are greater than or equal to 5. And in fact, they're greater than or equal to 10. So we're okay. So this essentially says, yep, that probably is okay to use as a normal distribution. But if we use the book's criteria, if we take n times p star times 1 minus p star, in this case, we have 25 times 0.6 times 0.4. And this equals 6, which is less than 10. So by the book's definition, the book would say, no, this is not normal enough to use. So just be aware that you could kind of get different, could potentially end up with different results. If it's not actually spelled out for you which one to use, then it is entirely at your discretion. You actually get to make the call. So that's why it's so important to show your work, because as you're showing your work, we'll get a sense of which one you used. So if you gave us this calculation and said it was acceptable, or these calculations are different enough that we recognize what they are, but nope, on a quiz or a test, it's entirely up to your discretion. And that's actually true. That's true not just in the test. That's true everywhere, but definitely on an assessment. If it's not specifically spelled out which one to use, then you actually get to make the call.